Welcome to the afternoon session. It's my great pleasure to introduce our first speaker this afternoon, Professor Richard Schoen. Professor Schoen is one of the most prominent mathematicians of our time, and he is considered to be one of the founders of at least two mathematical fields, geometry analysis and mathematical relativity. And he actually received numerous honors and recognitions for his fundamental contributions to the fields, including the solution of the Yamabe problem and the proof of the positive mass conjecture. And being a emeritus professor at UC Irvine and Stanford University, he's still working on the hardest problems of the field. So I guess he just doesn't want to just be a founder, but also finish of this field. So in fact, he's actually speaking today as one of the winners of the Frontier Science Award. So the title of his talk is Localizing Solutions of Einstein Equations. So let's welcome Professor Schoen.
Yeah, well, thank you, Mutal, for the introduction. Notice that he said working on, he didn't say solving the biggest problem. Is the sound okay? Did everybody hear? It feels a little echoey to me. Okay, so I'm going to talk about this FSA paper, which I'll describe. And actually, the paper is not real recent, so some of you have heard talks on this. I haven't spoken on it for quite a while, but I apologize if it's repetitive. But there are some new activity in the area, so I'll try to describe that. Let's see. Get this to work. All right. Oh, the other one. Oh, there are two sides. Okay. Yeah. So I'm gonna. These are the topics of the lecture, and at the end I'll talk about some more recent developments that things that have been done in the last few years. So the paper was published in 2016. It has the same title as my as the talk. Let me, just to motivate the problem, recall Newtonian gravity. So in Newtonian gravity, a massive object with mass density rho induces a force on other massive objects, which is proportional to the gradient of a potential function. So you have to solve this Poisson equation, assuming rho is, say, compactly supported. This has a unique solution which tends to zero at infinity, and then the gradient of phi is proportional to the force on a massive object. Okay, and so you could have situations where some regions of space are actually shielded from the gravitational force. So for example, if you had a spherically symmetric shell, then the interior would actually not be affected by the gravitational force. But if you take any region outside the support which extends to infinity, so which is non-compact, then it can never be shielded from the gravitational force. So in fact, to distant objects, the force is nearly rotationally symmetric about the center of mass. And so notice that if this is really very much related to the fact that rho is non-negative. So if rho were allowed to change sign, then this same result would not be true at all. And so the main result of the paper, FSA paper, is that in general relativity, even for vacuum solutions of the Einstein equations, this sort of phenomenon does not hold at all. So in fact, large regions extending to spatial infinity can be shielded from the gravitational gravitational field. Okay, so let me just quickly give a rundown of relativity. So, so this is really an n-dimensional theorem. So suppose we have an n+1 dimensional space-time, then the Einstein equations express the fact that the Ricci tensor minus 1/2 the scalar curvature times g is equal to a right-hand side, which is the stress energy tensor of the matter fields present. Now, in this talk, I'm usually going to assume there's no matter, so T will be 0 most of the time, and in which case the Ricci is also 0. So this is the Ricci is the Ricci curvature of the Lorentz metric on the space-time, and so these are the vacuum Einstein equations, which will be of primary interest to us. Okay, and so this is really an evolution equation. It's a hyperbolic system of PDEs in suitable coordinates, and so the solution is determined by initial data, which is given on a space-like hypersurface, or actually it could also be on a characteristic hypersurface. But so these pictures indicate that the gravitational field has finite propagation speed. So this point P is the behavior of the fields there are determined by data in the reverse light cone. And this is a picture of the light cone at a point. And so it's really an evolution equation. You start with initial data, which I'll describe. And so the initial data for the Einstein equations are the induced metric. So that's sort of the Dirichlet part of the data. And also the second fundamental form. So it's second order in time. So the second fundamental form plays the role of the time derivative of the field. And so these are the initial position and velocity. And so for the vacuum equations, those are the data. However, there's a little more to the story, namely the constraint equations. So the Einstein equation, the Einstein system is an n+1 by n+1 symmetric matrix of equations locally, and so there are that many equations. And so of those equations, n+1 of them actually can be expressed entirely in terms of the initial data. So, and those are called the constraint equations. So in order to even hope to have a solution of the equations with given data, these PDEs have to be satisfied. And so this is the scalar curvature of the Riemannian metric on M. So M is space-like, so the induced metric is Riemannian. This is the trace squared of the second fundamental form, and this is the norm squared with respect to the metric G. And this term, this is the divergence of a tensor constructed from the second fundamental form. So you'll recognize these equations as equations you learned in elementary geometry. These are a traced version of the Gauss and Cadazzi equations. So in order for a metric in a second fundamental form to be induced from a metric on a Ricci flat manifold, these equations have to be satisfied. So this is a system, this is a scalar equation, and this is a system of n equations. So they're n+1 constraint equations. And so in particular, the initial value problem can only be solved assuming these equations hold. And so the first thing you have to do is understand how to solve this system of constraint equations. And actually that's sort of the main, in a way, the main theme of the talk is how to understand solutions of these equations. Well, actually, obviously, there are many classical works on this. There are methods developed to solve these equations. Most of the methods involve so notice that it's a system of n+1 equations for many more unknowns. So it's a very underdetermined system. So you expect to have lots of flexibility in the solutions. In fact, classically, the methods for solving this involve fixing a certain number of parameters, particularly like the conformal class fixes the conformal class of the metric and imposes conditions on P to make it a determined system. And depending on how you do that, it's usually an elliptic system, nonlinear elliptic system, but not always. There are also methods which reduce it to, for example, a parabolic system. Bartnik has a method called quasi-spherical foliations. And so there are different ways to formulate this. The method, so what we're going to use to solve these is rather different. So the idea is not going to be to specify any initial data, but instead it's going to be to exploit the fact that the system is very underdetermined. Okay, so the fact that it's very underdetermined means you expect to have lots of solutions which do, sort of specified things. And so that's sort of the idea here. And so I just mentioned here with matter. So I'm not going to talk about matter anyway, so let me remove that. Skip over that. Okay, and so for the initial value problem for the vacuum, Einstein equations says that if I have an initial data set, M, G, and P, so G is a Riemannian metric, P is a symmetric 0-2 tensor. If they satisfy the constraint equations, then there's a unique local spacetime which evolves from that data. Okay, and it involves imposing a suitable gauge condition to make the problem hyperbolic, and then it's a matter of solving a system of nonlinear wave equations. Okay, and so I'm going to be interested in the talk in complete solutions which are what are called asymptotically flat. So this is a very natural class of solutions of the Einstein equations. It corresponds to what are called isolated systems. So if you model a finite distribution of matter or energy, and you assume everything else is infinitely far away, then you produce an asymptotically flat solution. And so the asymptotic flatness is the condition for the initial data that outside a compact set, the initial data looks like the trivial data. So the trivial data would be data in Minkowski space. So the metric G would fall off to the Euclidean metric, and the second fundamental form would fall off at some rate to 0. So it would correspond to a hypersurface in Minkowski space, which is asymptotic to some plane in Minkowski space. And so that's the sort of boundary condition, asymptotic flatness. And so the two basic examples of asymptotically flat spacetimes, which are explicitly, actually there are more, but the two that'll be of interest in the talk are of course, the Minkowski space, which is just the flat metric on Rn plus 1. So dx naught is my time coordinate. And the other one is the Schwarzschild spacetime, which is it's determined by initial data. So in n dimensions, we could take p to be 0, and the initial metric is a scalar flat rotationally symmetric metric on Rn. And so such a metric has to be, if we can write it in conformally flat form, it will automatically be conformally flat. The conformal factor here is a harmonic function. So that's the condition that the scalar curvature be 0. It's raised to the appropriate power, 4/n-2. And so this is it generates a vacuum solution of the Einstein equations, which models a static black hole. So the parameter E there is the mass or the energy of the black hole. So you can think of it as being the analog of the exterior field of a point mass in Newtonian gravity. Okay, and so for general asymptotically flat initial data sets, there's a notion of total energy, which can be computed as a flux integral. So I've written it here in n dimensions. This is a dimensional factor, and then it's the limit of some expression. So this boundary expression actually comes from the linearized scalar curvature. So if you linearize the scalar curvature at the Euclidean metric, then and you get a divergence, and the boundary term of that divergence is the term that it appears there, and you take the limit as R is large. And so the limit exists under quite general decay conditions. There's an analogous expression for the linear momentum, which depends on the asymptotic behavior of P. So I won't focus much on that here. Okay, and so there's an important limitation, if you like, or an important result about asymptotically flat spacetimes is the positive energy theorem. So it says that this energy, which was written on the previous slide, assuming the constraint equations, so assuming that the constraints hold, then the energy is greater than or equal to 0. And in fact, it's whenever the dominant energy condition holds. So if there's matter present, you have to assume the energy conditions. And it vanishes only for trivial data. That is data which is isometrically embedded into Minkowski space as a asymptotically flat space-like hypersurface. Okay, and so notice that yeah, in case P is 0, so if there's the second fundamental form is 0, then the assumption is that RG is non-negative. Okay, and so I'm not going to talk about the positive energy theorem, but let me just say that it is a theorem, and it's a sort of complicated story, but there are basically three methods, maybe even more now, at least in the three-dimensional case, to handle this. And so it was originally done using minimal hypersurface ideas by Yao and me, and then Edward Witten introduced the Dirac operator, which works for spin manifolds with the positive energy theorem. And then actually in the P equals 0 case in 3 dimensions, there's also an interesting flow proof of this, which is done by Huskin and Illman. It's called the inverse mean curvature. Actually, Richard mentioned it this morning in his talk. So it actually implies a little stronger result than the positive energy theorem. It's called the Penrose inequality. Okay, and so I'm going to now talk about the theorem we're going to prove. And so as I sort of alluded to, the Einstein equations actually lie somewhere between just the ordinary wave equation and Newtonian gravity. And actually for stationary solutions of the Einstein equation, they're like Newtonian gravity in that there's a sort of rigid asymptotic expansion. And so the question is, the question we want to ask is, what sort of behavior do we expect to be able to impose at infinity to produce asymptotically flat solutions for the Einstein equations? Okay, and so in the case of the wave equation, of course, if we take data in some Sobolev space or something, we can approximate it by compactly supported data. And so for many purposes for the wave equation, it's sufficient to consider data which is compactly supported for various estimates or whatever. The compactly supported data are a dense subset of the allowable data in that case. Now, on the other hand, for Newtonian gravity, the asymptotic behavior is actually rigid. It's determined by the Poisson equation. And the asymptotics near infinity, well, they include important physical terms like the total mass and the center of mass, but they're just rigidly determined by the asymptotic behavior of the solution of the Poisson equation. Okay, and so and so actually, so the thing that the Einstein equations have in common with Newtonian gravity is that embedded in the asymptotics near infinity are terms such as the energy, momentum, center of mass, angular momentum, if there's if that's non-zero. And so while these limit the sort of asymptotic forms which are possible, there are still lots of flexibility for the initial data for the Einstein equation. So they can't be compactly supported, right? You don't have data which is actually trivial near infinity because that would have zero energy. So it violates the positive energy theorem. So there are limitations on the data, but it's still somewhat flexible. So that's the basic theme of this talk. And so let me say a little more detail about the asymptotic behavior in order that the conserved quantities, the energy and the linear momentum, at least become well defined. And so it turns out this almost optimal behavior is that the metric and suitable coordinates fall off like x to the minus q, where q is bigger than, this is sort of half of the Green's function decay. So when q equals n minus 2, I'll call that Newtonian decay. So that would be the sort of decay that the Newtonian potential would have in n dimensions. So in 3 dimensions, it'd be r to the minus 1. And the second fundamental form, being a derivative, a time derivative of the metric, falls off one order faster. And of course, we always have to assume the constraint equation. So the scalar curvature is 0. So under these conditions, the energy and the linear momentum are well defined, and the positive energy theorem holds. And again, the positive energy theorem says that we cannot really localize data. We can't make them compactly supported. And so we're going to try to see what we can do. So actually, if you look more carefully at the positive energy theorem, it has a more quantitative description about how large the set of trivial, the set of points where the data is trivial could be. And so it turns out that actually, in 3 dimensions, you know, Ricci flat implies flat, but in higher dimensions, Ricci flat is a weaker condition. So it turns out the set of points where the Ricci curvature is non-zero has to be relatively large. And so that I want to describe that. So let me take U to be that set. So it's the open subset of M consisting of the points where the Ricci of G is non-zero. Okay, and then the claim is that assuming Newtonian fall off, so this is 2 minus n. So if you assume weaker fall off, then you'll get a weaker result. But I'm just going to look at the Newtonian case here. Then in this case, the set U, where the Ricci curvature is non-zero, has to be relatively large near infinity. So it has to occupy at least a fixed fraction of the boundary of the ball of radius sigma. So if you take a very large ball, there has to be a fixed fraction of the area of the boundary on which the Ricci curvature is not zero. Okay, so that's a more quantitative statement than saying that the solution can't have compact support. It can't be flat outside, or even Ricci flat outside a compact set. And so let me just indicate it. This is actually quite an easy theorem to prove if you rewrite the energy. So it turns out there's another expression for the energy in terms of the Ricci curvature. And so you can replace that boundary term, the term on the sphere, which I wrote down in coordinates, by a coordinate-free expression, namely the Ricci curvature in the normal direction, the metric, and then there's a factor of sigma, and then again, the limit as sigma tends to infinity, and this is a dimensional constant that appears out the front. Okay, and so this formula for Newtonian or for Schwarzschild type fall off was due to Ashtekar and Magnon, and actually it can be extended to hold for the most general asymptotic behavior in all dimensions. So if we take this expression for the energy, we can rather easily prove the statement that the Ricci has to be non-zero a lot of the time. And so what we can do is if the data is non-trivial, then the energy is positive. And so if we take sigma sufficiently large, then this boundary integral is at least E over 2, say. On the other hand, it's bounded above just by a constant times the absolute value of the Ricci. And then if using the decay assumption, so if we assume the metric decays like Euclidean plus terms of order 1 over r to the n minus 2, then the curvature involves 2 derivatives, so they'll decay like 1 over r to the n. And so the Ricci will have decay, which is like 1 over sigma to the n on the boundary of the ball of radius sigma. And so this expression becomes sigma to the 1 minus n. And so you get the lower bound on the sort of density at infinity of the set where the Ricci curvature is non-zero. Okay, and so so that's a more quantitative consequence of the positive energy theorem. Okay, and so the main theorem of the FSA paper is that this is essentially sharp in that you can always localize the data outside a cone. So a cone near infinity has this volume growth property, and so it's a sort of partial converse to this result. Okay, and so you can generally ask the question, what are good asymptotic forms for initial data for the Einstein equations? Well, we can't find data with compact support. So one thing you might expect to do, and which has been done a lot in the literature, is that if you consider the Schwarzschild spacetime, then by considering suitable slices in there, you can produce data which has arbitrarily specified energy and linear momentum, well, assuming the energy momentum vector is timeline positively directed, you can achieve any such things. And so people have assumed that a natural asymptotic form would be that the solution is asymptotic to a slice in the Schwarzschild data. And in fact, there's an earlier theorem which really was the start of this sort of gluing type theorem that I'm going to discuss, which was done by Corvino and me, and also Crucial and Delay. So what we proved is that you can, in fact, if you look at the set of initial data, which are identical to a boosted slice of the Kerr. So it turns out you have to, if you want to localize the data to a Schwarzschild slice, it doesn't quite work. You have to also allow some angular momentum. And so the Kerr solutions allow also angular momentum. And so what the theorem here is that the set of initial data which are identical to a slice in Kerr near infinity are actually dense in the set of all data. So you can take any asymptotically flat data with suitably good decay, and you can always approximate it by data which outside a compact set is an exact Kerr slice. So it gives you an exact asymptotic form, and the set of such data will be dense. You can approximate any reasonable data by data like that. Okay, and so as I said, we're going to prove a theorem about localizing data in a cone. So we're going to consider asymptotically flat data, and actually I'm just going to talk about the case when the scalar curvature is zero. So that's the constraint equations when the so-called Riemannian case, when the second fundamental form zero. So so let's assume we start with data which has the asymptotics of the type which gives us finite energy, and so Q check is bigger than n minus 2 over 2 and less than or equal to the Newtonian case would be Q hat equals n minus 2. So in the paper with Carlotto, we showed that there's a metric G with scalar curvature G identically zero, and which agrees with G hat inside a cone based at a suitable point. I'll have a picture on the next slide. And which is exactly Euclidean outside a cone with slightly larger angle. And so moreover, the metric G is close to G check in a topology in which the energy is continuous. So in fact, the energy is arbitrarily close. The energy of the localized solution is arbitrarily close to the energy that we started with. Okay, and so actually in our proof we lost a little bit of decay. So we take, this is true for any Q strictly less than Q check, and I'll talk about that issue later in the talk. So this is the picture. So we have this asymptotically flat solution, and so this is meant to indicate that in the compact part the curvatures may be quite large, it may be quite complicated. But if we take a point very far out, near infinity, and we look at a cone, even with very small angle, we go far enough out, then that cone will contain the high curvature part of the solution. And on the boundary of the cone, the solution will be pretty close to Euclidean. Of course, how close is important detail. But if we then think of choosing the vertex there, and then we try to localize in this cone. So we have a transition region, which is the region between the two cones. I've called it omega. So there's a theta 1 and a theta 2 cones there, and we have to add a little bulb there just to handle the various terms. And then there's an omega interior, so it's called omega sub I, and there's an omega exterior. So in the exterior, we want to make the metric flat. We want to make it Euclidean in the exterior, and in the interior, we want to leave it alone. So we're going to keep the metric fixed in omega I, and then there's this transition region, the shaded region there that it will have to transit. But the metric can be as smooth as you want. So we can choose any degree of smoothness, and the scalar curvature will be identically zero. So of course the metric is not analytic, right? This is not really a traditional elliptic sort of construction at all, where solutions tend to be analytic. And so we're really the theorem really exploits the underdetermined nature of the constraint equation. So it's really the fact that there are a lot more unknowns than there are conditions. So in this case, there are scalar curvatures as one condition, and you have the choice of a metric. And so there's a lot of flexibility in that. Okay, and so you can ask, well, what happens to the energy? So the energy has to be, as I've said, the energy is about the same as that which we started with. And well, in the original metric, just going back here, if I consider a cone with very small angle, then if I take that as my center point, then near infinity, that's only a very small fraction of the sphere. And so when I compute that boundary integral, the amount of energy in the original metric is quite small. It would be a small fraction of the, well, assuming that the energy is sort of uniformly distributed to start with. Say you started with a solution which is asymptotically Schwarzschild or something, then you would have very small energy in the cone. And so in particular, the total energy in the end has to be about the same. So that suggests that you can't impose too much decay in this region only. It doesn't say that the decay has to be faster than Newtonian. So if we started with Schwarzschild, say Newtonian decay, it doesn't say it has to be strictly slower than Newtonian, but it says at least the constant would have to be quite large, depending on the aperture of the cone. And so, in fact, in our theorem, we actually gave up a little bit of decay on that region. And so most of the energy, most of the energy would reside in that transition region. We took a very small angle cone. And so this shows that you can't impose too much decay. So in our case, we gave up a little bit of power. But since the paper was written just in the last 5 or 6 years, there have been results which actually do achieve the Newtonian decay, assuming you start with Newtonian decay. I'll talk about those at the end. But let's see. Okay, and so there are various applications of this. One is that you can construct solutions of the vacuum equations which are non-interacting. So you can take these localized solutions in a cone, and you can put two of them together, and you produce a new solution which in fact is a perfectly good solution of the initial data problem. So you can solve the Einstein equations, and these are superimposed in such a way that they don't interact at all for a fixed time period. So for example, I could take two arbitrary solutions, I could localize them in cones, and then I could just put them together, and that, because this is just Euclidean, is a valid initial data set. And so those solutions, when you solve the Einstein equations, will be completely non-interactive for a fixed time period. Of course, eventually they will interact. Okay, and so let me also mention, I might go a little quickly through this part, but so there's another sort of geometric aspect of scalar flat metrics or initial data that these ideas contribute to. And so let me just mention that in general relativity, geometric aspects of the initial data are very important for the space-time behavior. For example, the Penrose singularity theorem shows that if the initial data has an outer trap surface, so that would mean a well, you could think of it as a minimal surface in the scalar flat case, then such a surface would lead to a space-time singularity. In general, it would be a surface whose mean curvature vector points outward, so it'd be like a bubble. It's the neck of a bubble. And so similarly, the minimal hypersurface proof, the work that Yao and I did, has something to do with minimizing or stable hypersurfaces in the initial data. So in asymptotically flat manifolds with zero scalar curvature. And so there's a geometric theorem that if you have an initial data set with strictly positive energy density, so if you assume, so in the p equals 0 case, it would mean the scalar curvature is strictly positive, then in fact there can be it cannot have an asymptotically planar stable minimal surface. And so the constructions we have made show that without the strict condition, that's not true. So those solutions that are localized in a cone, of course, it's Euclidean in a half space. And so there are lots of Euclidean planes which are stable minimal surfaces. And so you can ask whether, and so similarly, so the notion of trapping, it's the slide. So in general, the condition on an outer trap surface would be the condition that the mean curvature plus the trace of p is 0. So if p is 0, then it's just a minimal surface. And so, for example, the horizon of the Schwarzschild is a stable minimal surface. And Penrose's theorem says that if you have initial data that contains any compact, any closed outer trap surface, then in fact it leads to a singular spacetime, an incomplete solution. Okay, and so you could ask whether these examples show that you can certainly have asymptotically planar stable minimal surfaces or MOTS in these in these initial data, and so you can ask the question whether there's any sort of geometric restriction on such things. And it turns out that while the Euclidean planes that appear in these solutions are stable, of course, they're just planes in Euclidean space, they actually don't minimize area. So they're not area minimizing. So in other words, if you go sufficiently far out in the plane, there will be a smaller surface which cuts the non-flat part of the solution. And so this was proven in 3 dimensions by Chodash and Eichmer. It's in the 3-dimensional time symmetric, that's p equals 0 case. And then it was very recently extended to higher dimensions by Eichmer and Thomas Kerber. And so actually the higher dimensional case is a little different. You do have area minimizing hypersurfaces in general, but they prove there are none which are limits of what are called isoparametric surfaces, closed surfaces, which are minima for the isoparametric problem. So you need some additional condition, some sort of strict, stronger volume minimizing condition in higher dimensions. Okay, and so notice that our proof of the minimal surface proves the positive energy theorem in 3 dimensions even implies that if the space-time had negative energy, then there always would be an area minimizing surface. So this condition really distinguishes between positive and negative energy. Okay, and so let me just briefly talk about some of the features of the proof. And so the idea is, so it's a kind of perturbation idea, and so in fact it's based on so the first step in this, which actually goes back to the situation considered by Corvino in the late 90s, is you can ask the question, suppose you have a set, say some open compact set in a three manifold or an n manifold, and suppose you have data on the set which doesn't satisfy the constraint equations, but it almost does. Okay, so suppose you're quite close to satisfying. So for example, you could have a metric on a three manifold which has scalar curvature which is quite small. So it's not zero, but it's quite small. The question is, can you perturb the metric with compact support? So in other words, keeping the metric the same on the boundary of the set, can you perturb it to make the scalar curvature zero? So that's sort of the basic question. And again, you can't always, it turns out you can't always do that because, for example, the positive mass theorem. So if you took a metric on R3 with very small, you perturb the Euclidean metric a little bit, you make the scalar curvature is very small. You cannot correct that to make it zero with compact support. It would violate the positive energy theorem, right? And so understanding the obstruction to doing that is really the first step in the procedure. And so it's the same kind of idea here, except it's a more complicated, it's not a compact set, it's a more complicated transition region. And so but the proof again involves, so we have first this picture, and then we just take we just use a cutoff function to join our given metric, which I'm still calling G check, to the Euclidean metric. And I do that with a cutoff function, which is a function of the angle. So it's a smooth cutoff function. It's 1 on the interior region so that the metric agrees with G check there. And it's 0 on the outer region, so the metric agrees with the Euclidean metric out there, and there's the transition in between. So phi is just the angle function. Okay, and then we have to correct it. So because we've chosen the point which is quite far out, this metric G tilde that I've defined, of course, it doesn't have zero scalar curvature, but it's pretty small. Scalar curvature is, point-wise small, and it decays suitably. And so the problem then is to correct it. And so we're going to correct it just by adding a small 0-2 tensor H, and that H is going to have to be compactly supported. So it's going to be supported in that transition region omega. Back. So remember, there's the outer the part outside the cone, which is where we want the metric to be Euclidean, the part inside where we want the metric to be the same, unchanged, and then there's the transition region, omega. And so that transition region is really the key. And so we're going to just write the scalar curvature as so the scalar curvature of G would be that of G tilde, and then plus a linearization, and then plus a quadratic error term. Okay, so L tilde is the linearization of the scalar curvature map at the metric G tilde. And so we want to solve that equation. R of G is 0, and we want to do it where H has compact support and is sufficiently smooth. So we want H to be, CK for any given choice of K. So that's what we have to do. And so we have some equations. The linearized operator written here is it's a double divergence, and then this is the Laplacian of the trace, and then there's a lower order term. It's a Ricci of G tilde given one, and then the key thing is, so we're trying to solve L tilde of H equals something. Well, it's a nonlinear equation really, but the linear problem would be the showing that L tilde is surjective in some appropriate spaces. And so in order to check that, we have to check the adjoint. So the surjectivity of an operator is equivalent, so for appropriate operators, is equivalent to the injectivity of the adjoint. Okay, and so the key thing is the adjoint operator, which I've written here. So that's a sort of Hessian operator. So its domain is functions, because the image of the operator L tilde is the space of functions. And so it's a Hessian, and then there's a Laplacian term, and then there's a U times a Ricci term. Okay, and so we need to prove the injectivity, strong injectivity property for the adjoint. And so actually, because the solutions of this problem, it's a very underdetermined system, it's useful to look at the fourth order operator, which is L tilde star. So that's a kind of biharmonic operator. It's written there. And then if we can prove surjectivity of that operator, of course, that implies surjectivity of L tilde. Okay, and so we're going to solve it using a Picard iteration scheme in suitable spaces. So the spaces have to impose appropriate decay at infinity and also rapid decay near the boundary of omega. So on the boundary of omega, we want H and a very large number of derivatives of it to be zero. So we need solutions that decay very rapidly near the boundary of the conical boundary of the transition region. And so there's a sort of strong coercivity condition that's really key to this. So we call it the basic estimate. And so we can first prove this strong coercivity estimate, which says that if we take for any positive s, so s is the decay of measures the decay at infinity, and we can estimate the second derivatives with decay minus s. S is positive in terms of L star view, where we decay 2 orders faster, but we have the zero derivative there in omega. And so the important thing about this estimate, which makes it work, is, well, there are two things. One is of course, the decay at infinity, and the other is the fact that there's no boundary condition imposed, no boundary condition on U at the finite boundary points. Okay, and so that's really what allows us to. So that sort of very strong coercivity is what allows us to solve the original operator with rapid decay near the boundary. So that's the idea. And it's the same sort of idea that's used in the earlier work, but it's somewhat more complicated because it's a non-compact transition region. There are really two different sorts of decay, and so basically. The dual space of the space H0 minus 2 minus Q is this space, and that's basically just because of this Schwarz inequality. And so the point is that this space here. So in our proof, it's important that this dual space have some decay. So 2 plus Q minus N has to be positive in order to use the basic estimate. And that's why we needed Q less than N minus 2. So if we started with Newtonian decay, then we would have to reduce the decay a little bit to make this method work directly. And so if we make that assumption, then we get this strong coercivity statement. And actually, this one isn't actually true for Q equals N minus 2. So you have to do something a little different to fix that decay issue. Okay, and so I can't go through the details, but basically the injectivity of L star implies surjectivity of L, and because of the fact that there's no boundary condition required near the finite boundary, you can produce solutions that decay rapidly there, and so H has compact support it vanishes to high order at those points. And so you could make it decay like this, and then once you have estimates on the linearized problem, you can use a Picard iteration scheme to solve the nonlinear problem. So that's the idea of the proof. And so again, the main technical issues that we encountered here are that the transition region is non-compact, and so you have to prove these sort of Poincare type inequalities in these, for these on these non-compact regions with suitable decay. And the second thing is the fact that there are two different decay rates. So the decay at infinity and the decay near the finite boundary. Okay, and so so let me talk now. Let me just close by talking about some more recent work on this. So there's a paper. Actually, there's a series of papers. The first one is in 2021. And so these authors, Zaratakis, Zimak, and Rodniansky, introduced a method called the characteristic gluing problem for the vacuum Einstein equations. And so the idea here is that we're solving the constraint equations on the space-like hypersurface. So this paper exploits the fact that if you take a characteristic hypersurface, then the constraint equations simplify. So they actually reduce to a family of ODEs. And so what they did is they first localized on a characteristic hypersurface and then solved the Einstein equations to produce the localization on the space-like hypersurface. One advantage is they are able to get they are able to do it without the loss of the Newtonian decay. And so they're also, by the way, in the same paper, they're able to reproduce caterpillar. He doesn't like to talk. Okay, they're able also to reproduce the work, the asymptotically Kerr work, using this idea as well. And in fact, they've done a number of things with this method since then. And so you say that this idea was further refined recently by Kale and Unger to produce novel C2 solutions. So these seem to be limited in regularity. They're black hole solutions which have interesting behaviors. That's a relatively recent work, which also uses this characteristic gluing problem, gluing method. And then let me also mention in a very recent work of B and P LeFloc, they deal directly with the space-like constraint equations, and they're able to sharpen our work in the conical gluing and refine the method to produce the optimal asymptotic. So there's a very recent paper on the archive which describes that. I haven't really gone through all the details of it. Okay, and finally, I have one more slide, but let me just say that as I mentioned, part of the sort of starting point of the gluing methods for the space-like case was the sort of local problem. So the problem of understanding the obstructions to deforming the constraint operator. So if you have a given data which doesn't satisfy the constraint equations and you want to perturb it so it does, you need to understand the obstructions to doing that. So there's a kind of local theorem that goes into it. And as far as I can tell, the characteristic gluing method would probably not work for that. I don't see how there would be any method. So the global consequences, follow from that method. But I don't think it really does the local result that actually is also rather useful in applications. But let me just mention just recent work of a recent student of mine. So as I mentioned, the basic idea of solving the localized gluing problem is understanding the flexibility in deforming, say, the scalar curvature, or more generally, you could do the constraint operator with deformations that are compactly supported. And so the obstruction is again, can be understood locally. So there's an analogous question for manifolds with boundary. So remember, a lot of interesting spacetimes have boundaries, which are, for example, horizons, mots, and things like that. And so there's another rather natural local deformation question, which is the problem of understanding the flexibility of deforming. So the simplest case would be the scalar curvature inside and the mean curvature on the boundary. So the natural boundary condition involves the mean curvature. So for example, if you're looking for a black hole space-time, then that means it would have, say, zero scalar curvature and zero mean curvature on the boundary. So if you had something which is close to that, then you can ask the question, is it possible to deform with compact support to achieve the conditions, those, adding the boundary creates quite a lot of complications. And I have my student, Hongyi Sheng, successfully solved that problem in the case of the scalar curvature and the mean curvature, just in a paper that was posted recently, earlier this year. And so I think that's also a natural sort of local gluing problem to consider. So just wanted to mention that, and that's the end.
Are there any questions?
Say it again. Can I do a family of solutions, or? I think so. So if you had a family of data and you wanted to perturb continuously, say you want to make them simultaneously solutions, they're approximate solutions. Yeah, I believe that you could do that. The solution. So you're basically picking out a unique solution with given decay. So if you impose a fixed decay rate, which also varies continuously in the family, I think you could produce a family of corrected solutions. A solution which minimizes, which has optimal sort of decay constant. Yeah, I don't know. That's probably, I mean, I guess you could give bounds on what the decay constant could be based on the total energy. And so, yeah, so if you assume Newtonian decay to begin with, let's say you assume the initial solution is asymptotically Schwarzschild or something, then the amount of energy, or that boundary term in the angular region, would be the corresponding fraction of the energy that you started with, because it's evenly distributed. And so then in the decay region, when you deform, you could say that the decay cannot be faster than some fixed constant, depending on the cone angle. So there would be estimates. Whether you could optimize that, I don't know. That might be tricky.
Any other question?
Yeah. Oh, yeah. I'm sorry, I didn't hear. So,
Yeah, I just want to hear.
the last
Yes.
the last part. Yeah. So again, you can try to do that problem by looking at the corresponding fourth order equation. The difficulty is that you need to specify the boundary conditions, and so the boundary behavior is so again, there are obstructions. So the obstruction has to do with the metric being static and the boundary being umbilic. So if you assume that those aren't true, then you can prove the corresponding injectivity result for the adjoint operator, but you have to do it with the appropriate boundary conditions. You have to impose the boundary conditions on the boundary surface, and those involve, it's quite a complicated set of conditions. sort of mixed Dirichlet-Neumann kinds of conditions that occur. Mm. They want you to use the microphone. Yeah.
Yeah.
Yeah. Well, I can't answer the numerical question, but I assume for numerical purposes, you would probably want to assume the asymptotics are as simple as possible. So probably asymptotically Schwarzschild or something like that. And so I think numerically doing this localization would probably be quite hard because it uses, it's, yeah, it would be hard to implement that. So my guess is that for numerical problems, you would want to assume the simplest asymptotics, which would be Schwarzschild, and that's justified, I think, by the earlier work. I mean, essentially any data can be approximated by such data. But I guess you're interested mostly in very simple data so that you can actually do it numerically.
Okay, so let's congratulate position 4 and thank you for the